project manager at Spectrum. I'm here today with Elton Williams, Nicotera, Hartman, and Hatfield. Go up script real quick in the beginning since they're running quick. So I'd like to thank Thank you, Ming, Dr. Nguyen. She was the physics supervisor for our project. It was about a little more than a year ago. We were in her lab, and I was watching these two quantum physicists wasting their time doing hand calculations on a piece of paper, trying to figure out the spectral line width of their laser from their analog optical spectrum analyzer. And I said, there's got to be a better way. This is ridiculous. So I poked around a little bit, and there wasn't. So engineers being engineers, sit around, and about a year later, you come up with a better way. So that's what we're going to tell you about, and hope you enjoy. It's going to be quick. There's a lot to push through. So what is an optical spectrum analyzer? Well, an optical spectrum analyzer looks at the spectrum of optics. So optical frequencies are way too high for electronic measurement. This one's green, but red laser is around 450 terahertz, very high frequencies. Oh, there it is. There's my red laser. Yeah, 450 terahertz. Can't put a wire on it and measure it. So we use something called a scanning Fabry-Perot interferometer, which basically uses optical resonance to probe the frequency spectrum for power intensity. So then we have an optical spectrum analyzer, which uses this interferometer, sweeping the mirror spacing between changes the resonant frequency, look at the output of a photodiode against voltage or current, and we can actually see the optical spectrum. So turn it over.
There are many current problems with the analog test system that is used by the physics department, one of them being cost. The system is very expensive. Another one is precision. There's no way to quantify the data. I say this because the data is graphed on an oscilloscope, and on the oscilloscope it's graphed as voltage over seconds. There's no frequency component to look at the frequency component of the spectrum. The third problem is usability. Usability of the system is so bad that it takes so long to get data and do a scan and quantify data. And the final thing is analog. Things like drift and other small analog problems occur. What we were looking to do our solution was duplicate the existing functionality. This is being done by doing a digital approach. Our digital approach will not only duplicate the existing functionality, but reduce the cost. If we can duplicate the functionality and reduce the cost, that already renders the analog system useless. Another thing that we were also searching out to do is make the system more usable and make it more accurate. If we can make the system more usable and more accurate, that really improves on what's already being done. So we're doing this by having a high voltage scanning. It's approximately 0 to 500 volts, which creates a scanning ramp that's used to basically scan the resonance of the laser. And then we'll be taking a current from a photodiode, and then that current will then be used to graph and then show to the user. So our approach for doing this is taking a digital value. That digital value will then be sent to a D to A converter and a high gain and high voltage amplifier. The high gain and high voltage amplifier creates the ramping function that I mentioned earlier. Then we will take the current from the photodiode, and then that current will go into a variable gain amplifier. From the variable gain amplifier, we interface to a high-speed A to D converter. From that A to D converter, we get a digital value back. The digital value will be cleaned up and filtered using a control module, and then we would interface with a real-time embedded user interface. A real-time embedded user interface will take inputs from the user based on scanning parameters for the laser, and then it will take the data values and graph them. Well, after we graph the data values, we can then manipulate them. So our approach for doing this was a top-down approach. It was using different modules. We have 4 modules and a chassis, so technically 5 modules. In these 5 modules, it's very safe to say that we have used almost every single area of electrical and computer engineering, and that's what made this project so difficult. So rather than us try to explain technically what's going on that's outlined in over 250-page report, we have a short video that kind of summarizes the detailed design, implementation, and testing that we will show. And after this video, we will go into testing and results.
it didn't work, go back and fix it many times. One of 2 PC boards we laid out for the project and built and soldered. The other PC board. High voltage jam.
Don't worry, we don't show all 5,000 copies.
120 pages of code in our report.
Chassis, final construction and test. This is actually being used.
So there you go. And 120 seconds, a lot of work. But okay. So testing that, I guess, is what all you guys actually want to know. So there you go.
So now that we completed our design, we needed to test it. But first, before testing the entire system, we had to break it down into modules and make sure everything actually worked before running high voltage 500 volt DC. So we started by testing things like the FPGA using test bench simulations. The input module, we ran a USB interface that would get digital values and then compare the analog values with the digital. The photodiode variable gain amplifier, we used an LED reverse bias to act as a photodiode, and then used an Arduino to change the voltage gain. The high voltage amplifier, we used things such as dummy loads, voltage dividers, and then we tested we used a independent SCR probe bar and a vacuum relay to test and make sure that things would safely shut down. For the user interface, hardware interface, we used serial terminal emulation, where we could test various inputs and receive the outputs and verify their functionality. And then for the GUI graphing system, we ran performance benchmarks to make sure that the performance was actually in real time and could be utilized safely. Then finally, for the chassis, we gave it a rough ride in Jacob's car to make sure it didn't fall apart. So for the high voltage output, we got an extremely linear gain, which is exactly what we wanted. The blue dots represent the actual data that we got, and the dashed line, which is actually unnoticeable because it's underneath it, is a linear approximation of these data points. Our performance benchmarks ran more than acceptably. The lower graph is a normal computer system. It's a dual-core processor, and then the top graph is the Raspberry Pi. The Raspberry Pi is a cheap little computer. It's $35, and it was graphing between 10 to 20 milliseconds. The variable gain amplifier was extremely linear, which is exactly what we wanted. The top line is the piece by simulation that we ran, and everything else is the actual amplification. And as noted, it is extremely linear, which was a pass for us. And then finally, for our FPGA, all our test benches passed.
So after we got all our modules to work as predicted, we just took the whole thing and took it to the lab and replaced the analog system with our digital system, and it replicated the outputs. As you can see on the next slide, the peaks were shown, the overall graph on the bottom, and the top view is of the zoomed in 2 peaks we were looking at. So the initial results were promising, and now our platform is ready for advanced improvements and further research. So mission success. For accounting, we spent about $3,000. We spent $1,500 in the first semester on testing and pre-design, And in this semester, we spent about another 1,500 on building the circuits and putting it together. So that took about 670 hours, a lot of work done, and the pie graph shows our modules time spent.
Now, during the whole process of building the system, we learned quite a few things along the way. We actually have 5 pages worth of lessons learned, but we're not going to go through all those. We're just doing a couple of highlights here. For number 1, if once is nice, measure it twice. If you only want to cut and drill something once, make sure your measurements are correct. Then, before you send out the PCB to make it built by a company, you want to make sure that the PC board is correct. You don't want to do any sort of alterations once it comes back from there. It's not easy to do, and it's a lot of extra time you don't need to be wasting on it. Also, protect your board against any problems you might have with voltage concerns or current draws that may happen if an unknown component that you're working with might accidentally break or it suddenly explodes up on you. You want to make sure that the rest of the PC board isn't compromised if something like that happens. If you have to repeat something and it is incredibly annoying to do so, there's probably a better way to do it. Stop, find a better way, do it that way. It's going to save you some stress and probably a lot of time along the way. Then you also want to make sure, if you can, use programming tools and chips that you're familiar with. Chances are you already have the chips, you already have the tool, you know how to program it, and it's going to save you a lot of time. You can get started on programming right away. Any change that you make to a small part of the module, make sure you check the entire module that the rest of it is still working, because any change you make might have unexpected consequences for the rest of it. You want to catch any of those unexpected consequences early on. Versions, especially for programming, especially when you have over 5,000 lines of code. You want to make sure you save versions. Have a working one. If you get that, save it, document it as working, make a copy, work on the copy. If you get stuck, you can always go back to the older version. And finally, always have a plan B and even a plan C for those just-in-case scenarios, because those will happen. And as the bottom line, this was a challenging project, and we were able to complete it for the senior design project. We were able to use many different areas that the ECE department taught us, from signal processing to FPGAs to microcontrollers to control systems theory. And using all of this knowledge, we were able to make a product that not only met the requirements that we set out to meet, but we were able to deliver it to the customer within the time that we were given. So we're hoping that the DOSE framework will open up new doors for the people working in the research and frequency domain and the optical spectrum analysis. So that's back to you.
Thank you.